Welcome to Theory of Computation class. Today I give an introduction about a Turing machine. Alan Turing has introduced a mathematical model called a Turing machine in the year 1936. If you consider a Turing machine is a mathematical model which is used to design a language and also it is used to compute integer functions in it. The integer functions may be a simple addition, subtraction and multiplication operations. So these operations can be done with simple integers in a Turing machine. So it's a basic mathematical model. And this model also contains two notations. One is a finite state control and infinite length of input tape. So if you previously consider a finite automata and a Pushton automata, those two are also a mathematical model, but it contains a fixed length of an input tape. But a Turing machine contains an infinite length of input tape. And we already know that input tape is divided into cells, and each cell only one symbol will be represented at a time, and only one symbol will be read by the finite state control at a time. It is also available in the Turing machine. So this is the model of a Turing machine. So at a time a finite state control is available at a particular state, then it will read the cell in an infinite length of tape. Initially, all the cells in an infinite length of tape contains a blank symbol which is represented with a notation called capital letter B. So capital letter B represents a blank space. And from x1 to xn, this is the valid input string. So this input string will be pasted at any location of an infinite length of tape. So from this x1 to xn only the finite state control can be moved. So it can be moved either left direction or right direction. So the movement can be varied by the finite state control. So at a particular one movement, there are three activities will be done. One is there may be the possibility of change of state with the current input symbol, and there is a possibility of replacing one symbol with another symbol on a tape. So this is only the new phenomena in a Turing machine. So if you consider a finite automata and Pushton automata, the input tape is only a read-only format. But a Turing machine contains a read and writable format. So what are all the input symbols which is stored in an infinite tape, that will be replaced with some other symbols. So after replacing all the input symbols in an input tape only, the finite state control will be moved to final state. So at a time, there may be the possibility of changing the state, there may be the possibility of changing a symbol, and also we can able to move the direction, either forward direction, that is called as right direction, reverse direction means left direction. So this is the basic functionality of a Turing machine with a finite state control. So input contain a collection of cells. Initially all the cells contains a blank space and few input symbols will be stored at a particular location. And the input string values, that means a finite state control head can be moved to left to right or right to left for scanning. So initially the tape head points to the first symbol of input string in a cell. In one move, a Turing machine, depending upon that symbol which is available in a particular tape, it may either moved to left direction or right direction with the change of state, or it may stay in the same state also. So we can also use to print a symbol. So this is the notation, that means tilde of Q0. So the input of Turing machine is two symbols. One is the current input state with the symbol available in a tape, and there are three output notations are there. One is the replacement state, that is instead of Q0 the control head points to Q1 state. Then instead of A, I can replace the tape symbol with X. So second parameter is the tape symbol, first parameter is the state. So this is the tape symbol and this is the direction. Only two direction is there. Either we can move to left or right direction. So see here, right direction is a forward direction, left direction is the reverse direction. So this is a generalized form. So I just revised the basic concepts of finite automata, push-on automata, and Turing machine. So if you consider finite automata, which contains two input symbols, so one is set of state with the current input symbol, then it goes to state. So the output is only one parameter. If you consider PDA, which contains three parameters, one is the current state, then current input symbol on tape, and the topmost value on stack. So depending upon it, the output will be varied. So either it goes to new state. With push operation means the second parameter contains two values. If it is a pop means it contains epsilon symbol. If it is stop operation means only one symbol at the second parameter of output. So this is the PDA basic methodology. If you consider Turing machine, it contains only two input values. One is current input state with the current symbol, and it has three output notations. That means it can able to move to a new state, then the replacement symbol on tape with the direction. So this is the basic difference between these three models. So if we consider the definition of Turing machine, it is like a push-on automata. So push-on automata is also contains 7 tuple representation because push-on automata is implemented by using stack. So the same notation is available here, but in a Turing machine there is no usage of stack. Instead of that, the tape symbols are denoted here. So here tau denotes tape symbols, but in a PDA tau denotes stack symbols. That is only the difference. So Q is a finite set of states, sigma is the input symbol, tau means the finite set of symbols on tape, tilde is a transition function which contains two input parameters and three output parameters. Q0 is the starting state, blank space is the symbol which is initially stored on tape. So this is the tape symbol. F is the final state. So these are all the 7 parameters of Turing machine. And I give the overview or a comparison of the three basic model. One is finite automata, another one is push-on automata, and the third one is Turing machine. Finite automata can be implemented by using a regular expression or a regular grammar. So that regular expression and regular grammar are comes under a type 3 grammar. So if you go for a Chomsky hierarchy of language, type 3 represents regular language. Then the input for push-on automata is a context-free language which comes under type 2 language. And Turing machine supports unrestricted language, so type 0 grammar is supported under Turing machine. And finite automata and push-on automata has a fixed length of tape. But a Turing machine can be implemented with infinite length of tape. And in a finite automata and push-on automata, the control head can move only to forward direction, but in Turing machine, it can move to forward and backward notations. That means the movement can be forward or reverse method. And in a finite automata and push-on automata, the tape symbols are only readable format, so there is no replacement is implemented in finite and push-on automata, but Turing machine contains read and writable format of tape, so we can replace one symbol with another symbol on input tape. So type 3 supports regular language, type 2 supports a context-free language, and type 0 supports unrestricted grammar. So its corresponding language is given here. And input tape is read-only format, so there is no replacement in both FA and PDA. Replacement possible means read and write operations are possible on tape. And stack is only used in push-on automata, and that does not be supported in finite automata and Turing machine. And this is the input and output format of transition function for these three notations. And language acceptance means when the finite automata accept a language means the tape should come to end of the symbol and the final state is reached means that finite automata go to accept state. Push-on automata can go to acceptance states with the two format. Either the stack may be empty, or if the final state is reached, then the push-down automata stop its process. And the Turing machine only comes to the end when replacing all the tape symbols with another replacement symbols, then it will go to final with accept state. And types of FAR, NFA, DFA, types of PDR, NPDA, DPDA, and types of Turing machines are deterministic and non-deterministic Turing machine. So this is an overview of both these three models of mathematical notation. And instantaneous description means we can able to read every symbol of an input string with a current input state, and if the input string is correct, the Turing machine will automatically go to final state. So that is the definition of instantaneous description. So idea of Turing machine is defined in terms of reading the entire input string with the current state. For example, if you take an input string as alpha, beta, gamma, and beta is the present state of a Turing machine, then the entire input string is splitted as alpha and gamma. So the first symbol of gamma is the current symbol A under read or write operations. Then gamma is a subsequent symbols of input string. The string alpha is a substring of input string and it is formed with the symbols A. So it is the instantaneous description notation. So TED of Q xi, which is equal to PYL, where Q and P are set of states. So here the first parameter of input and the first parameter of output are set of states. And the second parameter of input and also the second parameter of output are the tape symbols. And L is represented for a direction. So another direction is R. So this is the moves in Turing machine. And if you consider language of a Turing machine, this is the definition. Let M is a Turing machine which accepts a language L, means it is denoted as L of M. So language contains a sequence of strings. Another name of string is called set of words. So for reading all the symbols at a particular string, then the Turing machine will automatically go to final state. So it is the generalized definition of language of Turing machine. And these are all three main topics which will be covered in a Turing machine problems. The first problem is conversion of context-free language to Turing machine. And the second one is computation functions. So I already told the Turing machine definition. A Turing machine is a mathematical model which is used to define a language and also used to compute integer functions in it. So these two first 2 points are the explanation of those definitions. And few programming techniques are also available on Turing machine. So I will give the explanation of the conversion of CFL to Turing machine and the second and the fourth techniques in future videos. Thanks for listening.